Hey, let's talk a bit about section 1.3, Introduction to Functions. So functions are a very big deal in mathematics. Most of our semester will be spent talking about functions, different properties of very specific types of functions. But for now, we're going to talk about functions just in general. So start out with a definition. So we've got that a function is a relation in which each x-coordinate is matched with only one y-coordinate. That's the important part. Each x-coordinate is matched with only one y-coordinate. Okay, so it's a relation, right? So it's a set of ordered pairs so that every x-coordinate is paired with exactly one y-coordinate. So let's look at some examples. Is it a function? So here's one. So let's have it in roster method. So 1, 2, maybe. Let me make that look a little better. 1, comma. And then 3, 4, maybe 5, 6. Okay, so here we have a set, right? We know it's a set because we got the little curly brackets, and it's a set of ordered pairs, right? So it's a relation, so check mark, we got it. It's a relation, great. Now we need to verify that each x-coordinate is matched with only one y-coordinate. So we look at each x-coordinate and say, okay, 1 is our first x-coordinate. And is it paired with anything else? Well, no, it's just paired with 2, right? And we go to this one, 3 is only paired with 4, 5 is only paired with 6. So these are only paired with one y value. So we would say, yes, it's a function. All right, that's kind of squiggly, but we get the idea. It says function. Function. Okay, so that one is a function. Great. Let's have another one. Maybe 1, 3, 2, 3, 3, 3. Okay, so we do the same thing. Is it a function? So first we verify it is a relation, right? It's a set of ordered pairs. Now we need to verify that each x-coordinate is matched with only one y-coordinate. So we go to each one of these. 1. How many things is the number 1 paired with? Well, it just goes with 3, right? 1 does not appear as a first coordinate in either of these. So 1 is only paired with 3. 2 is only paired with 3. 3 is only paired with 3. So this is a common one that we want to say is not a function, but it is a function, right? Because none of these x values are repeated. And that's going to be kind of how we tell. If we're given a list of all the ordered pairs, if we repeat any of these x values, that's going to indicate to us that that it's not a function. So this no repeats for x, so this means that yes, it is a function. F-U-N-C-T-I-O-N. Maybe it is a function, right? So now maybe an example of one that's not a function. So how about 1, 3, 2, 4, 2, 7. Okay, so we look at this one and say, yes, it's a set of ordered pairs. Yes, it's a relation. That's great. But then we notice that 2, the number 2, is paired with both 4 and 7. So 2 goes with 4 and 7. So we say not a function. Okay, so more or less, we're looking for repeated x values. Now let's take a look at another form of these things. So we're going to want maybe to think about it like this later. And if I wrote it like this, where we kind of showed one that looked like this in a previous section, where we have all of our x values over here, and these are y values over here, and we indicate that they're paired together with arrows. And when we write it like this, we can tell it's not a function if 2 arrows come out of one number, right? So this one number has 2 arrows coming out of it, so this is not a function, right? If it is a function, then each one of the values over here on this side and the x values is only going to have 1 arrow coming out of it. Okay, so let's look at a few more that might be a little more difficult for us. So how about something in set builder notation? What about the set of all, I don't know, x comma 3, such that -2 is less than x is less than 4. Okay, so we want to know if is this a function? So it's the set of all ordered pairs that look like this, where y is, or excuse me, yeah, the y coordinate has to be 3. So for any of these ordered pairs, the y coordinate is always 3, and the x coordinate must be between -2 and 4, not including those endpoints, but everything up until those. So let's draw a graph. So I want my x values to be between -2 and 4. So I'm going to choose everything between -2 and 4. But we have to have y coordinate 3. So any point that's on this graph, maybe we can just pick some things that are between here. So if I pick 1, then the point 1, 3 is on the graph, right? If I pick the point 2, then 2, 3 is on the graph. So any number that I choose between -2 and 4 is going to give me a point up here on the graph that is on this, looks like a horizontal line, right? So be careful with these when you're graphing them. If you have to graph them on the computer, use open endpoints here when we have a strict inequality, right? My x value has to be strictly between -2 and 4. It can't be equal to -2 or 4. It's got to be strictly between those. So we could draw that picture. How great. Okay, so now we can look at this. We have a whole bunch of ordered pairs. For any x value we choose, we're only going to go to a y value of 3. So any x value we put in there only goes to one thing. Any x goes or is paired with 3. And that's only one thing, right? So we would say, yes, this is a function, right? So if our y value is fixed at 3, and every x value can be chosen between -2 and 4, hey, that is a function. Okay, what about another one like that? So maybe the set of all -1 y, such that -1 less or equal to y less than 2. Okay, so let's draw a picture of this one. We're going to have kind of the same idea as we did for the one above this, but now we're not free to choose what our x value is. Our x value must be -1. So -1 has to be our x value. And -1 is going to be paired with all of the numbers for y that are between -1 and 2. So -1 is here, 1, 2 is here. So every y value between 2 and -1 is going to get paired with the x value -1. We're going to have a solid dot on the -1, right? Because we're non-strict inequality, we could be equal. But any other y value between here can be chosen, right? So we got a vertical line here. So it looks like here -1 is paired with lots of stuff, with all the numbers between 1 and 2. So it's not a function. Okay, great. So all right, we can tell if we've got a function. Let's run through what we just did. So if we've got a list of ordered pairs, all we're looking for is repeats in the x. So if x repeats, then we know it's paired with more than one thing. If we're given more of a mapping diagram like we had there with arrows, we're going to tell if something's a function or not by how many arrows come out of each of the x values. When there are more than one arrow coming out of an x value, that means it can't be a function because it's paired with more than one thing. And then our little set builder notation thing, we could draw a picture to correspond with this. Now, yeah, good. So this is right where we are. That's wonderful. Something that we should notice is that this line segment is vertical, right? And if I have a vertical line, then I'm going to have one x value, here in particular -1, is paired with a whole bunch of stuff, right? So maybe look at another example here. If I've got one that's not a function, and maybe we can think about the one or something similar to what we had above. So here are my ordered pairs, and if I plot these, I got 1, 2, I got 1, 3, and I've got 2, 4. Okay, so we decided up above that this was not a function because we repeated these x values, right? One is paired with both 2 and 3. So graphically, what's happening here is that I've got these 2 points are on a vertical line. So any 2 points on a vertical line share an x value, right? So if that's the case, and I have 2 points that are on a vertical line that belong to my function, then I know that those 2 points share an x value and they're going to have a different y value. So that means it cannot be a function. So let's write this in a maybe more concise way. A graph is, or maybe represents, a function when any vertical line, it can only intersect it one time at most. A graph represents a function when any vertical line intersects the graph at most once. Okay, so we could write this is phrased in a positive way. We could also phrase this in a negative way. We could say that a graph does not represent a function when any vertical line intersects it more than once. We could write it like that if we wanted to, but it means the same thing, right? So if I give you a graph here of maybe that, and it goes on and on forever here, right? What we're going to do here is just picture in your mind all of the vertical lines in the world imposed right here on top of there, right? Any one of these is only going to intersect this picture once. So we say that this is a function, right? Because any vertical line intersects at most once. Well, what's the other side of that look like? Maybe if we drew it like this, the other way, right? Now I can exhibit one vertical line right here that's going to intersect it once, twice, 3 times. So we have shown one x value paired with more than one y value. So this is not a function. So essentially, yeah, if you can draw any vertical line on the picture that intersects it more than once, it's not a function, and then we're done. So let's talk real fast about one of the kind of gotcha sort of things. Let's look at a graph here. Maybe let's have an open dot here, and it goes like this. And then there's a closed dot here, and it goes like this. Okay. So our temptation here is going to say that this is not a function, but it is. Remember what the closed dots and the open dots meant, right? So this point is on the graph, and this point right here is not on the graph, right? That's what those open dots mean. We mean that this branch of the graph here is going to go all the way up until that point and get as close as you want to it, but it's not going to be exactly on that point, which means that if I draw a vertical line right here, it intersects right there, but there's no intersection here. So that means that this one is a function, right? So be careful with these. When we have an open dot versus a closed dot, be careful with that, because the vertical line is only going to intersect the graph where the graph exists. The open dot means the graph does not exist at that point. Okay, great. More definitions. Suppose f is a relation which describes y as a function of x. Okay, that's great. The set of the x coordinates in f is called the domain. We've probably seen these words before, right? All the x values are called domain. All the y values are called range. We're usually not going to have problems with the roster method. So let's look at just one of those. 1, 2, 3, 4, 5, 6. So here's a relation. It's a function. Great. We already talked about it. We would say what the domain is. Well, it's the set of all the x coordinates. So it's just 1, 3, 5, right? 1, 3, 5. And then the range here, range is going to be the set of all the y coordinates. So we got 2, 4, 6, right? And that's it. And if you're saying, man, is it that easy? Yeah, it's that easy. So something that we might make an error on here is if we have repeated y values, maybe. So if I have maybe 1, 2, 1, 2, or 2, 2, 3, 2. For this one, our domain is going to be still, again, the set of all the x values. So I got 1, 2, 3. And then my range, though, is 2, 2, 2. Well, it's just 2, right? And we remember from the first section when we were making a set in a roster, or writing explicitly the elements of a set, we don't repeat. So it's just 2, right? That's the only thing in the domain. Now let's look at what, because we're going to be wanting to talk about diagrams sort of like this later. Let's look at this. So this, 1 goes to 2, 3 goes to 4, 5 goes to 6. So here we would call where all of the arrows originate, this is our domain, and where all of the arrows terminate, this is our range. So what this one would look like, we would have 1, 2, 3, we got 2, they're all just going to 2, right? So yeah, that's it. Great. So we can find domain and range from roster method or a graph. Okay, so these are going to be the ones that are going to be difficult. When it has a roster method for you, that's going to be easy. But if I'm given a graph, maybe let's do this from here to here to here. We got a nice little arc there. How beautiful. Let's say that that's -1. No, let's say that that's -2. Let's say that that's 2, and let's say that that's 1. Okay. So here is here's our relation, right? We know it's a relation because it's a set of ordered pairs, right? A curve on the plane is a set of ordered pairs. And we just need to know what the domain and what the range are. So the domain here is the set of all the x values. So when we're looking at x values, we don't care what the y values are. So the trick here is to think about just squishing everything down to the x-axis, because we only care about what the x's are, right? So all these ordered pairs, we just want all the x values from all these ordered pairs. So we squish it all down to the x-axis. And if we did that, it would lie right there, right? We would have a line segment between 2 and 2. So we can write this as an interval, right? We know that we're going to include -2, so we use a bracket. We know that we're going to include +2, so we're going to have a bracket here as well. So we can write that as an interval, or we could write this with set builder notation if we want to. But this is probably going to be a more cumbersome thing to do for us, and this is going to be preferred because it's easier to look at, right? It's less busy for our eye. Okay, so we can do the same thing with range, right? And let's do that, the same thing with range. So if I'm looking at my original graph, now we only care about the y values, right? Now we only care about the y values. So we can do the same thing. If we squished everything over to that y-axis, that's going to show us where the y values of these ordered pairs are, right? So this point here gets squished over to the origin. This point here also gets squished over the origin, and all of this stuff would be shaded, right? So now I want my range. Well, looks like everything between 0 and 1. And we can write this, in step builder notation as well. Less or equal to y, less or equal to 1. Okay, and that's it. Here we go. All right, what's going to be difficult for you is when we have maybe this thing broken up into pieces, or maybe we've got open dots and closed dots happening. So let's do one of those. So I got open dot, closed dot, boop. And then maybe let's do closed dot to an open dot down here. Bloop. All right. So now I want to know my domain and range. So just to be clear here, this is the point 2, -3. This is the point 0, 1. Here's the point 0, 2. Here's the point -2, 0. All right, we can do the same thing here, right? Our domain is going to be the set of all of the x values. So if we took all of these points and we just pushed them all to the x-axis, see where it overlaps. So starting on the left here, if I move this down, I'm going to have a closed dot here, and I'm going to have, following this branch, it's going to go all the way along that negative x-axis, all the way until 0, and then that open dot is going to get pushed down here. But we also have a closed dot at x equals 0, so that closed dot is going to fill in that blank. And then we could do the same thing here, right? Going forward, or excuse me, toward the positive direction, we're going to push everything up. So we're going to have a line segment here, and then we got an open dot right there. So here, our domain would be -2 all the way until 2. And we're going to include -2, but not include 2, right? Because we've got an open dot on x equal 2. And we could write this in step builder notation, but this is what the computer is going to want, and this is preferred anyway. So maybe we'll just leave it to you to know that we can write that in step builder notation as well. All right, so now we want our range R, and we can do the same thing, right? If I get rid of all of this, I want to get rid of the orange. Go away. Okay, so now instead of pushing everything to the x-axis, we can take everything and push everything to the y-axis, right? So let's push everything to the y-axis. This gets moved here, this gets moved here, here. All of this stuff gets moved to the y-axis, so we got an open dot there, and all of this stuff is shaded. So we have our range now. We just need to read the interval, right? So we would go from -3, not included, all the way up to 2, not included, right? Because they're open circles. And again, right, we can write this in step builder notation too. Okay, maybe just one more, because maybe we can have one more. Yeah. So let's have this one goes. And let's have that it approaches this line, but it doesn't ever get there. So maybe like that. And then this one's going to go down forever. Okay, so we can do the same thing with this, right? Listing our domain. We can visualize this in our heads, right? If I took everything, all of these x values, and we pushed, or excuse me, all the ordered pairs, and we pushed them all down to the x-axis, because that's really what we're looking at, we would have an open dot here that would go this way forever. And we would have a closed dot here that would go on and on this way forever. So this one is going to have a domain that comes in 2 pieces that we're going to need to connect with a union, right? So this is going to give us one interval. That's -infinity all the way to -1, not including either endpoint. And then we need the other branch too. So that's going to be a union. And now I see that I've run out of room. What a bummer. But that's okay. We would go from 0 to infinity. So that's not exactly out of room. Okay, so yeah, our domain comes in two pieces because our branches are separated, right? So now we can do the same thing again for the y coordinates or our range, right? And let's do that. So if I looked at all these ordered pairs, and now I want to push them all to that y-axis, right? Everything's getting pushed to the y-axis. So I'm going to have a closed dot here. It's going to go down, 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 down forever. And our x, this other branch here, this is something we're going to have to be careful with, right? What this dashed line is, we're going to call that an asymptote later on. But this is a line that the graph is going to approach but never, ever touch. So if I squished everything over here, it's not going to touch here at 2, but it's going to get all the way up until there, right? It's going to have everything between there. So for our range here, we've got our range is split up into two intervals as well, right? We've got this one right here, so that's negative infinity all the way to looks like -2. We would include -2 but not infinity. And then we would want the other branch of this, so that's from looks like 0 to 2. Not including those endpoints, so we would use parentheses. Okay, super. So we can find domain and range if we're given an explicit list of points. We can find domain and range if we're given like a little nice diagram like this, or we can find domain and range if we're given a graph. We just need to think about what are the x coordinates, what are the y coordinates. All right. So here is another type of exercise here. If we are given an equation, we want to know whether or not the equation defines y as a function of x. So really, let's take a look at one here. So y equals 3x plus 2. We could draw a graph of this if we really wanted to, but that's not the point of the exercise. What we want to know is just this, right off the face of it. Does y represent a function of x? So another way to ask that is, how many y values are you going to get if I plug in any x you want? So for any x, how many y's are there? So in particular with this one, 3 times x plus 2 is going to be y. So if I had any number at all, and I multiplied it by 3, how many numbers are you going to get? Well, if I multiply 2 by 3, I get 6, right? I don't get two things, I get one thing. If I multiply a number by 3, I'm only going to get one thing, right? So this is only going to give us one number. And if I add 2 to that, well, hey, I'm only going to get one number as well, right? Any number plus 2, that's a unique value, right? 4 plus 2 is 6. 9 plus 2 is 11. It's not two things, it's one thing. So we just kind of have to think through our heads. If I put in any number I want here, how many numbers are you going to get out? Well, this one, we know that multiplication is well defined, so it's only going to give us one thing. Addition is also well defined. That's only going to give us one thing. So we would say that, yes, this is a function. So I think that what would be the best example here is something that is not a function. So maybe if we have, let's have this one. So we want to know how many things, how many y values for each x, question mark. So something that made this one convenient was that it was already solved for y, right? And we can just kind of go through the x stuff and say, well, how many numbers am I going to get out of that? How many numbers would I get with this step? So let's do that first here. Let's solve this for y. So if I'm going to solve this for y, we want to get y alone, right? So the first step is going to be to subtract x squared from both sides. Okay, and now I've got y, the y stuff alone, but I would have to do that square root business, right? I would have y is plus or minus square root of 1 minus x squared. All right, So this is equivalent to this. And another way to say that is they represent the same thing, right? So I can look at this one. Well, if I put in maybe, if I put in the number 0, how many things are you going to get? So if we say x equals 0, what's going to happen? Y is plus or minus square root of 1 minus 0, which is plus or minus 1. So there are 2 y values that go with x equals 0, exclamation point, right? So that's not a function, right? I have one specific x value that we've just shown that has 2 y values that go with it. So we're going to say that this is not a function. So once we get to this point right here, we can kind of see ahead what's going to happen. There are going to be values that are going to give us 2 y values, right? There are x values that are only going to give us 1, maybe say x equal 1, right? If I put 1 in there, I'm going to have that y equals plus or minus square root 1 minus 1 squared, which is plus or minus 0, but that's just 0, right? So this x value did only give us 1 y value, but there exists x values such that that's not the case, right? There are x values that exist that are going to give us 2. Long story short here, without blabbing too much more, we're looking for this plus or minus business, right? If that is present, then we know that we're going to be able to generate more than one y value for certain x values. All right, so that's it for section 1.3. If you have any questions at all about anything, please let me know. Otherwise, have a great rest of your day.